Module 5, our last module. Yeah. So the topic here are advanced data structures. So far at this point, we didn't use some relatively advanced data structure. We only use array, right? So far, you can see our main data structure is array. Yeah, very simple. Yeah, but in our last module, I'd like to introduce some relatively more advanced data structures. Because later, in future, when you do problem solving in the real world, sometimes you may need to use advanced data structures in order to solve some relatively hard problems. Yeah. So in this module, I plan to introduce two advanced data structures. The first one covered in part A and B, heap data structure. Then we will use it to do a heap sort. Yeah. So part A, part B, both heap sort. Yeah. So in one part we cannot complete. Yeah. So we approximately we need 1.5 part lectures, 1.5. We complete this topic. Yeah. All right. So today part 1, heap sort. First, let me give you a short introduction to this heap sort. So why we need to create a new algorithm, another sort algorithm. So far we have 5, right? Selection sort, bubble sort, insertion sort, merge sort, quick sort. This one, number 6, heap sort. Yeah. So the same old sort problem, yeah. But this time we have some new consideration. Sorting with special requirements. Yeah. Not the general requirements. General requirements, heap, for example, what we learned last time? Quick sort. Yeah. General requirement, right? Yeah. But sometimes in your real world application, sometimes you need to impose some special requirements. Yeah. Not just do general sorting, but you need to set a few special requirements when you solve the sorting problem. Yeah. Here, let's look at, so what are those special requirements? Yeah. First, we need to avoid that bottleneck problem. Remember the bottleneck for the worst case. Yeah. In our sorting problem, the bottleneck, the worst case, when the worst case in big theta of n squared, that's the bottleneck. Okay? Yeah. The 5 sorts we learned before, 4 of them have the bottleneck. Only merge sort does not have this bottleneck problem. Merge sort, its worst case is in big theta of n log n. The other 4, okay? Selection, bubble, insertion, quick sort, they all have the bottleneck problem. Okay? So first requirement, we don't want to have this bottleneck problem. All right? Yeah. Yeah. The second one, in place. Here, when I said in place, I mean algorithm in place. Okay? Not the element in place. In place, I'm talking about algorithms. What's that? Yeah. In the last part, I explained this concept. When we say an in-place algorithm, that means the extra space used. Yeah. Remember the extra space. What's the extra space? The space used other than input output. Input output, so we treat as the standard. So you have to, all algorithms, you have to use, storage space to store your data for input output. But other than that part, that's the extra part. Yeah. So for in-place algorithm, we mean the extra space used is in big theta of 1, okay, bounded by certain constant. That's the in-place sort. So you cannot use too much extra space. The space you used when your data size is larger, your extra space also becomes larger. Then it's not an in-place algorithm. If the algorithm is not in place, so you use relatively more memory space. For example, the merge sort. Merge sort, we know, it's not in place. Merge sort. Remember, when we do the merge, we need to use auxiliary two arrays, two subarrays, right? Auxiliary. Then we, do comparison. Our destination, not auxiliary two sub, auxiliary destination array, right? When we merge two ordered arrays, we need an auxiliary destination array to put elements in place. That auxiliary array, much larger than the constant. Yeah. So it's not in place. Yeah. So another situation for in place. Yeah, because sometimes I give you concept questions asking you, so which of the following algorithms is in place? For example, our first question in homework assignment number 2, right? First question, which of the following algorithm is not in place, right? Yeah. All right. So here, because later we may have similar questions, for example, in the final, right? In the final, I may give you similar questions. Yeah. So here, I want to give you another part of the information about in-place algorithms related to recursion. Yeah. Because some of our algorithms we need to implement using recursion, right? Yeah, recursion. And many algorithms we need to use recursion. Okay? Yeah. So when you use recursion, you need to think about the extra space you need to use. Recursion, right? Because I talk about the internal implementation of the incursion in computer main memory. There is a stack we need to use, right? How to implement recursion inside computer memory? A stack data structure. The stack data structure, does it use the extra space? Stack structure, right? Stack, yeah. And the stack structure also uses extra storage space. But the stack could be deep, very deep, right? Yeah, think about the depth of the stack. If you use recursion, your algorithm, you need to use recursion, then you need to consider the stack data structure used to store your data, your temporary data, right? How much memory that stack is used, you need to consider for extra space. Okay, the stack you also need to consider for that extra space. Yeah, but usually the stack sometimes could be very deep, very deep. Then that situation it's not in big theta of 1. How can you control the depth of the stack in bounded by constant? You cannot, right? How can you control the depth of the stack, right? Yeah. If you cannot control, then it's not in place. If you can control the depth bounded by constant, then you can make it in place, right? Yeah. But to do that, you need to do some management work. Yeah, it's possible, but you need to do some special management work to reduce the depth of the stack. Yeah. So here, that point. If you do nothing, if you just use recursion directly, yeah, in general, it's not in place. That algorithm is not in place. Okay? Yeah. Here, I give you, this, explanation. Yeah, because sometimes people may ignore that stack hidden because that data storage used is hidden. You cannot see it, right? In the formula, you cannot see it. Yeah. So many people may ignore that. Yeah. But the hidden part, the extra memory is used in a hidden way. You cannot ignore. All right? Yeah. No. So that's the in-place explanation. The third one, maintain dynamic data efficiently. What's that? Yeah, this is a new requirement we need to understand. Dynamic data first. You should know the dynamic, right? Data comes in and update it and delete it, in a dynamic way. Yeah. So in the real world applications, actually your data, many times your data is in dynamic. Yeah. Comes in and goes away, yeah, in a dynamic way. Yeah. Then think about when you need to use your data structure to maintain the dynamic data efficiently. So what do you mean, maintain efficiently? When you insert a new data, how much work you need to do to insert a new data? When you delete a data, how much work you need to do to delete the data and recover? Yeah, because when you do insertion, deletion, you need to recover the structure of the structure of your data stored in your database. In your data structure. Okay? Yeah. Here, I can give a simple example. For example here is, if I give you ordered array, if you arrange your data as ordered array, when you insert a new data item, you need to do some work to make sure after the insertion, the whole array is still ordered. We need to do a lot of work, right? Yeah, think about that. Still ordered array, after you remove randomly selected element in the ordered array, remove it, Okay, yeah. Then one position in the array is empty. That position is empty. In order to maintain your array structure, you need to also shift some of the elements, right? Yeah, because we know array elements must occupy consecutive locations in main memory, right? That's the array requirement. All right, so this simple example tells you when you store your data in some specific data structure, when your data is dynamic, you need to do some arrangement work. So that work, when you do arrangement work, that work, we want to make sure it's efficient. It's efficient. Yeah. Here you may ask question, what do you mean efficient? Right? Because this word is pretty vague, right? Pretty vague. Yeah. You need to pay certain cost. Yeah. But how much that cost is, you feel it's efficient. How much that cost is, you feel not efficient, right? Yeah. So here, give you a simple idea. Yeah. So in our algorithm, based on our experience, yeah, efficient usually we mean if the management work, recovering, that work you need to do is in big theta of log n, log base 2 of n. Then we say efficient. Okay, log base 2. Yeah. But so this is efficient. But if you do in big theta of n, then not efficient. Okay? Yeah. So log base 2 of n, it corresponds to the binary search type efficiency, right? Binary search type efficiency. Big theta of n, it corresponds to linear search type efficiency. Then it's not efficient. Yeah. That means if you need to use linear search, then we feel not efficient. If you can do binary search, then we feel efficient. Yeah. So that gives you the concrete description about the efficiency here. Okay, all right. Now you understand these three requirements. Next question. How do we design a sort algorithm to satisfy these three requirements? Yeah. Currently, our 5 sorts we have learned so far, none of them satisfies these 3 requirements. You can see, the merge sort not in place. Okay, the merge sort not in place. Requirement number 2, not satisfied. Okay, yeah. So you can see, All right, So let's continue our analysis. All right, So here, I explain idea. So we need a new, in order to get a new sort that satisfies these 3 requirements, we need a new data structure. That's the reason. We need a new data structure. All right. What kind of new data structure you need here? Remember our goal for efficiency, we need a binary search type efficiency. Okay? Then that you can imagine, in order to make our data arrangement fit in a data structure in the form of binary tree. Yeah. Binary tree. Then we can do the binary search, right? Yeah. So we need to consider our data structure should have certain binary tree structure. Yeah. So you arrange your data in a binary tree. Then you can, work on your data management using the log base 2 of n number of operations. So, yeah. All right, that's quite natural. Yeah. Then design of the data structure. Now we need to implement this idea. Yeah. But when we implement this idea, so here we want to store our data in a binary tree structure. So we need to work on a binary tree, right? This time, binary tree. So the next question is how to represent a binary tree. Binary tree. We need to find a simple way to represent it, as simple as possible. If the representation is very complicated, then we don't feel it's a good choice. Yeah. Too complicated. Question?
So
yeah.
when you're saying represent the binary tree as simple as possible, are you saying that the data itself needs to be as simple as possible with repeating values or something, or are you saying that it just needs the diagram needs to be as simple as possible?
The data, the relationship among the data. So data we can imagine as numbers, right? Integers, it's okay. Yeah. So data, yeah, it's not the data. But how do you arrange the data? Yeah. Binary tree, we know binary tree. Among the nodes, there must be some relationship, right? Parent-child relationship. How do you describe parent-child relationship in a binary tree, right? Yeah. 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 But we need a simple way to describe the parent-child relationship. That's the meaning. Okay? Yeah. 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 All right. So let's look at that. Any problem?
Is this the outlet one?
Yeah. Light. Oh, too dark?
The outlets aren't working.
Oh. Oh, outlet. Oh, that control your outlet?
I was asking. They're on.
All right. Yeah. Let me just keep going. Yeah. Next question. So you still need the.
It's not working.
Not working. Yeah. All right. So you can try other places. It's not this problem, right?
No.
All right. Now, let's look at the candidates. Yeah. We need to choose, underlying data structures to be used to support binary tree structure. Yeah. So our candidate at this point, yeah, one is array. We can use array to do it, right? Yeah. As a candidate, how to do it? Another question. How to use array to represent a binary tree? That's another question. Okay. Yeah. First, let's put here. Okay. All right. Another candidate, linked list. Yeah. We learned a linked list before, right? Yeah. Yeah. The linked list. The good thing is there are links, right? Yeah. Inside data structure, you can use pointers to to represent links, point to. So you can use pointers, links to, because in Java you don't have pointers. So you can, use references, point to, or link to some other nodes, right? Parent, child. So it looks like linked list. You can, at least you can represent parent-child relationship easily, right? The problem is linked list. So linked list is relatively complicated, right? Relatively complicated. So people want to avoid linked list. So if you can avoid, then try your best to avoid linked list. Okay? If you cannot avoid, then you have to use it. But here, we want to avoid it. We want to avoid it. So we want to use, because array we feel very comfortable, right? Array, so easy to use, very comfortable. The problem is how to use array to represent binary tree. That's a little challenging. We need to solve that technical problem. If we can find a simple representation of binary tree in an array, the underlying storage structure for our data is just a simple array, but we have some special way to represent a binary tree, then it's a good choice. It's a good choice. All right, so next we want to work on array. But this array is different from the way we use array before, because we need to put some special structure on our data. The way we use array before, we do not do anything on we do not assume anything on our data, right? We just store the data directly in array. But here, you have to do some work. You have to, put a special structure on your data. Now, so let's look at the next step. What kind of special structure we need to impose on the data stored in an array. Okay? All right. Binary tree. Binary tree structure. All right. Because if you do not make a binary tree structure, then not efficient. Binary structure, we know. So when we work from levels to level, different levels, the depth of the level, the binary tree. So we want to make a structure close to balance the binary tree. If the binary tree is not balanced, it's a skewed way, then the depth is pretty big. Then you cannot get a log base 2 of that. So we need a binary tree structure close to be balanced. Or later we will call it a near balanced. Near balanced. All right? So let's look at the next part. This time we will build a binary tree structure in an array. But when we build it, we want to make it as simple as possible. As simple as possible. So if your building way is too complicated, then not worth it. Okay? So we want a very simple way to build it. All right. Here, how to modify the array, or how to add some new condition on the data stored in an array so that we can remember the goal. The goal to represent a binary tree structure, we want to address parent-child relationship, right? The nodes inside binary tree, typically the parent-child relationship you need to represent. Yeah. Here, we need to represent parent-child relationship in a simple way. Yeah. As simple as possible. Yeah. All right. Data stored in array. Yeah. Yeah. If it's sorted, yeah, so here. Yeah. Because if you sort, sometimes people manage the dynamic data, they can use a way. Because at the beginning, the data size is relatively small, so people can sort it. People can sort it. Okay? Yeah. So relatively easy to sort the data. Yeah. Then the data is added more and more in an ordered array. Yeah. So we always want to keep our data in an ordered array. So every time when you insert a new data item, how much work you need to do. Yeah. So here. So if the data is not in order, then if you want to make it in order, you do insertion operation, right? Yeah. Insertion operation, yeah. If we use our standard insertion operation, remember in the insertion sort, we do standard insertion operation. You need to do this much work, big theta of n. Yeah. So that's as we said in the previous slide, not efficient. That's not efficient. We don't want to do in that way. Yeah. All right. So our goal, yeah, log base 2 of n. Yeah. The binary search way. Yeah. All right. The question is to get this efficient way for the insertion operation. Yeah. You need to insert a new data item in the binary tree, near balanced binary tree. Yeah, more specifically, near balanced binary tree. If it's not balanced, if it's skewed, okay, skewed. So, what do you mean skewed? Okay, suppose this is a binary tree. Binary tree. Also binary tree, right? That's not balanced. That's skewed binary tree. Okay? Yeah. All right. Yeah. So the linear search, binary search, yeah. When you do the management work, so we want to take the structure related to the binary search. Yeah. All right. The question, how to get it? Yeah. Yeah. This time we need to work on the data structure, the new condition. We need to set in our array to make it represent a binary tree. Yeah. All right. Yeah. Yeah. So next, let's look at what's the parent-child relationship. You need to define. How do you define parent, child? For the child, you have left child and you have right child, right? The binary tree, each node, you have up to 2 child nodes, right? Yeah, up to 2. Yeah. Sometimes you have 1, sometimes you have 2, sometimes you have 0 child. So these 3 possibilities. Each node, the number of child nodes, it may have 3 cases. 0 node, 1 node, child node, 2 child nodes. Yeah. 0, 1, 2, 3 cases. Yeah. 8.2, binary tree structure in array. Yeah. All right. How to build? Yeah. So that's the first technical question we need to answer. How to build a binary tree inside an array? Yeah. This time we need to describe this special data structure, this heap data structure. Yeah. All right. Yeah. So the heap, when we make this heap data structure, we still use the array as the underlying storage object. Yeah. Because we like its simplicity. Yeah. Array, so simple. Yeah. Yeah. So we want to keep the simplicity part of an array. Yeah. Then how to make the operation, not too bad. So we want this near complete binary tree. Yeah. Because in order to make a complete, the node number must be power of 2 minus 1, right? Yeah. That's too restrictive. That's too restrictive. Yeah. Because in general, the number of nodes n is not in the form of power of 2 minus 1. If it's not, but we still want to make it as close to complete binary tree as possible, so then we have this near complete binary tree. Yeah. The question, what do you mean near complete binary tree? Yeah. Here, let me draw this simple example to show you what's the near complete binary tree. All right. Here, in this example, you can see, other than the bottom level, this is the bottom level, okay? The bottom level is not a full. Yeah. Bottom level still, you have more positions, you can insert more nodes, so it's not a full. Yeah. But other than the bottom level, all the levels above the bottom level, they are full, okay? Yeah. All the levels above the bottom levels, they are full. Yeah. Then, if a binary tree satisfies this condition, we call it near complete binary tree. Yeah. Because in this way, the depth of the tree close to log base 2 of n, right? Very close to log base 2 of n. Yeah. All right, yeah. Yeah. All right, yeah. So, sufficient space for dynamic data. Yeah, so that's another. Yeah. Sufficient space. Yeah. So this point, a little tricky, because think about it. You need to store the data you need to store is in dynamic way, comes in and goes out in a dynamic way. How can you predict the data size? It's hard to predict the data size, right? Yeah. How much storage space you want to use to make it sufficient, right? Yeah. Yeah. Here, you need to solve another technical problem. How to manage your storage space to handle the dynamic data. So that's another technical problem you need to you need to solve. Okay, yeah. So we will look at that problem later. Yeah. All right. Yeah. But here we have two technical questions we can answer. First, parent-child relationship here. Yeah. Parent-child relationship. How to build. Yeah. Here we need to answer the question. Parent-child relationship. Yeah. All right. How much space is sufficient? Yeah. That's another technical question we need to answer. Yeah. Because nobody can predict it well, right? Yeah. Nobody can make a good prediction. Yeah. So you have to follow, you have to keep an eye on the data, keep track of your data. Yeah. When the data reaches the limit, storage limit, then you enlarge the storage space. Okay? Yeah. If the data is reduced in certain amount, then you need to shrink. Yeah. Things like that. Yeah. Enlarge, shrink, based on the amount of data you need to store in your data structure. That's the main idea here. All right. Yeah, so here, first let's answer that question. How to make array space sufficient for dynamic data. Yeah. Here I just describe the idea. Yeah. Describe the idea. Yeah. All right. At the beginning, we do not have an idea what is the size we want to use for our array at the beginning, right? Yeah. So you just, use some appropriate size. Yeah. Because at beginning, yeah. So you just use data to store initial data. Yeah. Assign certain amount of space to an array initially. Yeah. But quickly, you need more space. Yeah. Quickly, so you will reach the limit. Yeah. You need to enlarge. Yeah. But we know for an array, as soon as we declare an array with certain size, it's fixed, right? Yeah. The array, you cannot change it. After you create an array, you cannot change its size. Yeah. That's the property of an array. Yeah. Array size, as soon as it is created, we cannot change its size. Yeah. Here we have to follow that property. We cannot change its size. But what we can do, can we create a new array with larger size and copy the data from old array to new array and destroy old array? How about that way? Okay? So the idea, how to enlarge an array, we have to replace old array by a new larger array. So you need to create a new array with larger size, then copy the data from old array to this new array, then destroy old array to release the memory space used by old array. That's the idea we need to implement. Yeah. All right. Keep adding data and monitoring the size closely. Yeah. Because sooner or later, you will reach the limit close to the array size. Okay? Yeah. Close to the array size when the threshold is reached. But you need to do the transition work. Yeah, there is a transition work. You need to do the transition work before your data reaches the limit, right? Yeah. You need to do the transition work ahead of time. Not at the time it reaches the limit. That is, it's too late. You need to do a lot of transition work. Then your users need to wait a long time, right? Yeah. You don't want your users wait a long time. Okay? So you want to do transition work starting at some point, so you need to set a threshold. Yeah. For example, so what's the threshold? For example, if you reach the 90% of the limit, then you can start your transition work, right? Yeah. Yeah. You reach the 90% line, okay? You monitor, you keep, monitor the, how much space of the array is used, okay? As soon as it reaches the 90% line, then you start the transition work, okay? The transition work, you need to create a new array with larger size. So usually people use double the size of the old array, double size of the old array, okay, larger size. Then you copy the data from old array to new array, copy. After you completely copy the old data into that new array, you destroy the old array. Then, after that, you use the data from this new array. That's the transition step. Yeah. All right. Usually, it is expensive to copy a large array. Here, there is a problem. This transition could be very expensive because when you copy the data from old array to new array, it could be very slow. Think about it. If you have 1 million elements in the old array, when you need to copy that 1 million elements from old array to new array, how much time you need to wait, right? You need to make your users, wait there, okay? Until you finish the data copy, okay? Old array to new array. Yeah. That step could be very slow. Yeah. The question, how to avoid that? How to avoid your users' waiting time, relatively long waiting time, right? Yeah. So here you need to solve this technical problem gracefully, okay? Gracefully. You still need to do the work, but you do it in a smart way so your users cannot feel the waiting time. Your users cannot feel the waiting time, right? Yeah, that's a smart way. Yeah. Here, let me describe that special way. Yeah. Look at this peak graph. This means when you copy, so here, the vertical, that's the waiting time, response time axis. Okay? All right, so that, yeah, here. How much time when you copy the data, your users need to wait? Okay, all right. This peak means at this part, your users' waiting time jumping. Before that, waiting time very small, right? After that, waiting small. But when you reach the copy, sooner or later you need to do the transition. You need to copy the data. But when you copy the data, then the waiting time suddenly becomes very large. Yeah. There is a peak. Okay? Yeah. So now you want to avoid this bottleneck. So we treat this part. This is the bottleneck part. So we want to, reduce the height of the peak. Reduce it. Yeah. So the idea is pretty simple. Okay, remember we started a copy a little earlier. When we reach the threshold, 90% threshold, we start a copy. Yeah. We do not wait until the limit. So here, at the limit, you have to make the copy. Then your user need to wait a lot of time. Yeah. But we want to start early. We start a copy early. Okay? Before we reach the limit, we start a copy. But we spread a copy time in certain period. In this long period, relatively long period, we do copy. Okay? We do copy. All right. Yeah. Yeah. So here, for example, here I give you some idea. Okay? Yeah. All right. Suppose this is the point where we reach the 90% of the line. Right? Then when one new data comes in, one new data is in, so then we copy 10 items. How about that? Every time one data comes in, but we copy 10 items. When you copy 10 items, it does not take long, right? The waiting time is not that long. Okay, this is waiting time, not that long. 10 data item copy. So your users won't feel long waiting time. Okay? So then it's fine. Your users feel it's okay. So the second data comes in, another 10 copies. Another 10 data item copy. Yeah. But then 10% comes in, you copy the 100%. Because 10 times, right? You make data copy 10 times of the data comes in, right? So 10% comes in, you make 100% copy. You complete all copy, right? Whole copy. So here I just described the idea, okay? So in this way, you spread your copy time evenly in a relatively long period of time. How about that? You spread, okay? Then you won't have a peak. There is no peak type waiting time. How about that idea? Then your user, the general users, they won't feel relatively long waiting time. That's what we mean. We make the copy gracefully, right? Gracefully. Justin? Yeah.
So the idea is that you have an array that's already instantiated in the copy over and times the amount of items, the second array.
Yes.
Every time. So the second array, like since the size is static,
Double the size.
it's double the size.
Double the size.
Okay.
Yeah. Every time we double. When we create a new array, always double the size of old array, previous. Yeah. Because you have to use a fixed size, right? When you instantiate array. Yeah. Yeah. So then we use 90% line. I just use it as an example. Okay, you just choose the appropriate one. Okay. Then after reach the 90% line, you do 1 to 10 ratio copy. One data comes in, you make 10 elements move to the new array. Okay, 1 to 10 ratio. Then, after the remaining 10% comes in, you copy the whole 100% to the new array. Then you can destroy old array. Now you start use the new array. Just keep doing this process. How about this idea? Yeah. Okay. All right. Yeah. All right. So we solve this technical problem. Okay. Yeah. All right. Let's move to the next topic, 8.3, heap property. Heap property. But this time, we need to solve another technical problem. The first one, relationship among heap nodes, this time. How do you define parent-child relationship? Now, this time, we want to store a binary tree in an array. By imagination, because what you can see still an array. You won't see a binary tree directly, but that binary tree is an imaginary binary tree. It's not a real binary tree. It's an imaginary binary tree. Okay? Yeah. The concrete thing is still an array. Okay? What you can see is still an array. Yeah. But there is a hidden imaginary array, binary tree behind this array. Yeah. All right. Yeah. Node. Now we want to represent nodes inside the binary tree. Yeah. How do we identify a node? We use its index to identify a node. Yeah. Then, relationship between two nodes. How do we represent two nodes when they have parent-child relationship? We want to find a simple way to represent parent-child relationship. Simple way. All right, so here. Yeah. Because each node, how do we control the nodes? We use their indexes to control the nodes. Yeah. So to access each node, we need to use index of that node. Yeah. So when we define the relationship, we use their indexes. Indexes to define the relationship. Yeah. All right, so now let's look at the parent-child relationship. Yeah. So this is a typical situation. Parent node P represent the parent node. Then two possible child nodes. Capital L, left child node. Capital R, right child node. Yeah. So here you can see from the diagram, you can see the index of the parent node is I, index I in an array. And which node we treated as the left child node of the P, 2i. Double the index of the parent, 2i. Okay? So the node in this 2i location, that one we treated as the left child of that P node. Similarly, the node stored at this index 2i plus 1, that location, we treat it as the right child of the parent node. That's simple, right? Using the formula, these two formulas. In this way, we can represent parent-child relationship easily, without pointers, without references, just the simple math formulas. Okay? Yeah? All right. Yeah. But here, you can see we cannot use the node at position index 0. We cannot use. Yeah. The reason is because if you use 0 here, when you double the 0 is also 0. Then parent and the left child becomes the same node. We do not allow that. Okay? Yeah. So for that reason, we do not allow the parent node take the index 0. Yeah. So the smallest index you can use is 1. Okay? Yeah. So I must be greater or equal to 1. Yeah. So we leave the node as 0 empty. We do not use it. Do not use it as our heap node. Yeah. All the other nodes we can use, yeah, other than that 0 node, 0 position. Yeah. All right. Yeah. Okay. Yeah. So then, based on this parent-child relationship, we can, now you agree, you can build a binary tree in an array in the simple way, right? Yeah. You can build a binary tree in the simple way. Yeah. Very easy. Yeah. All right. Then 2 types of heaps. One is the max heaps, another is min heaps. Yeah. Maximum, minimum. Yeah. So for the heaps, when we arrange our data items in a heap, we want to put some properties for the heap nodes, properties. Yeah. So the max heap property, what's that? That means the value of the parent, A of I, so that's the value of the parent, greater or equal to the value of its left child, this is the left child, and also greater or equal to its right child. Yeah. If this property is satisfied, yeah, if the heap has this property, then we call it a max heap. It's a max heap. Yeah. For the min heap, yeah, then just opposite. Yeah. The value of the parent node is less than or equal to the value of the both left child and right child. Okay? Then the min heap, yeah, the maximum, minimum, yeah. So these 2 types of heaps, yeah, we can use. Yeah. All right. Now let's look at a max heap example. Oh, yeah. Let me complete this slide, then we finish today. Yeah. So look at this near complete binary tree, right? Yeah. Near complete binary tree. The node number, that's the array indices. This 1, 2, 3. These are the array indices. Yeah. Then the values are inside the circle. Okay. The values stored in this array inside circle. Now you can check our max heap condition. Yeah. You can see the value of each parent node is greater or equal to the values of both child nodes. Yeah. No violation. No violation. Yeah. But when we store the data, we use array. So here I use this array to show you how to store this heap, max heap data structure in this array. Yeah. So 0 position, no, yeah, we skip the 0 position. Then at a position 1, index 1, node with value 16. Yeah. Then it's 2 child nodes, node 2, node 3, with index 2 and 3, so 14, 10, yeah, so 2 child nodes. Then node 14, 2 child nodes, yeah, 8, 7, left child, right child, like that. Okay. Node 10, 2 child nodes, 9 and 3. All right. Node 8, 2 child nodes, 2 and 4. All right. Node 7, 1 child node, 1. Yeah. So in this way, you can see, yeah, we can use a simple array to store a heap data structure. That heap has the near complete binary tree structure. All right? Yeah. Yeah. So that's for our data structure part, our data arrangement part. Okay? Yeah. So here we haven't reached the point for sorting. We haven't reached that point for sorting. Yeah. We have several more steps preparation before we are ready for the sorting. At this point, we're not ready. Yeah. We just get started. We just, make our data storage right. Yeah. Yeah. That part. Yeah. Let me see how much time I have. Yeah. Yeah. I run out of time, so I have to stop right here. Yeah. So next time we will build a heap. After we build a heap, then we can do the heap sort. Okay? All right. Yeah. So let's complete it next time.